Welcome to 7 lectures on terpenes and terpenoids. In this lecture, we are going to discuss about the chemistry of farnesol molecule. We will see the occurrence as well as uses of farnesol. We will discuss the structure of farnesol on the basis of chemical methods of analysis. We will discuss two different methods of farnesol synthesis. Farnesol shows cis-trans isomerism. So at the end, we will discuss about the stereochemistry of farnesol. Now let us see from where we get the farnesol. Farnesol is present in many essential oils such as citronella, neroli, lemongrass, rose and balsam. It is used as a perfumery compound. Farnesol and its derivatives are starting material for the synthesis of natural products such as squalene molecule as well as the phytol molecule. For example, farnesol pyrophosphate is a biosynthetic precursor for the synthesis of squalene molecule, which is also a biosynthetic precursor for the synthesis of cholesterol molecule. Similarly, farnesol can be employed for the preparations of for the laboratory synthesis of phytol molecule, which is a diterpenoid. Now let us discuss the structure of farnesol. Structure determination of farnesol was initiated in the year 1913. At that time, the chemists were not having sophisticated tools and therefore they were relying on the methods of chemical analysis. The structure determinations on the basis of chemical analysis starts with the estimations of carbon and hydrogen. From estimations of carbon and hydrogen, chemists reach to the empirical formula, and from empirical formula, chemists reach to the molecular formula of the farnesol, and it was found to be C15H26O. Now, this molecular formula of the farnesol gives lot of information about the structure of farnesol. Here there are 15 number of carbon atoms. It means that there are 3 isoprene units, and according to the special isoprene rule, these 3 isoprene units may be joined through head to tail linkage. Now, since it contains 3 isoprene units, farnesol belongs to a class of sesquiterpenoid. Another information that we get about the structure of farnesol uh, from molecular formula is the degree of unsaturations or double bond equivalence. Degree of unsaturations or double bond equivalence is nothing but the how many double bond or how many ring the molecule contains, or it may be the combinations of ring as well as double bond. Now for a molecule CXHYOZ, the double bond equivalence is calculated by the formula x plus 1 minus y by 2. So if you keep the values of carbon and hydrogen here, the double bond equivalence is found to be 3. So farnesol show 3 degree of unsaturation. It means that farnesol molecule may contain 3 double bond. It may contain the 3 rings, or it may contain the 2 double bond plus 1 ring, or 1 double bond one two double bond plus 1 ring. That is a combination of ring plus double bond. So in the incoming investigations, we have to find out this nature of unsaturations or a degree of unsaturation. So to find out this unsaturation nature, hydrogenation experiment is performed. Farnesol is subjected to hydrogenation in presence of a catalyst, and after hydrogenation experiment, the product is again purified and it is subjected to elemental analysis. The molecular formula of the hydrogenation product was found to be C15H32O. Now, if you do some chemical arithmetic, that is, if we subtract the molecular formula of the farnesol from the hydrogenation product, we see that farnesol has consumed 3 molecules of hydrogen. Now, since it has consumed 3 molecules of hydrogen, it means that farnesol contains 3 double bonds. So, 3 degree of unsaturation in farnesol corresponds to 3 double bonds. Now, these 3 double bonds can be conjugated or it may not be conjugated. So, UV absorption spectrum is another data regarding the farnesol molecule. UV shows the lambda max around 192 to 196 nanometer, and since this value is not in the conjugated range of lambda value, it means that the 3 double bonds are not conjugated. Now another chemical arithmetic is related to this molecular formula C15H32O. The parent hydrocarbon of this hydrogenated farnesol corresponds to C15H32, and C15H32 is nothing but the CnH2n plus 2, and this is a molecular formula of the acyclic hydrocarbon, and therefore this farnesol molecule is a acyclic molecule. Now let us discuss the nature of oxygen. In this way we have completed the analysis of unsaturations and we have proved it contains the 3 double bonds. Now we have to find out the nature of oxygen in farnesol. So for that a simple experiment is performed. A farnesol is subjected to oxidation and the resulting product is having molecular formula C15H24O. Now analysis of this compound has shown that it is an aldehyde and it is called as farnesyl. Now oxidation, if we get an aldehyde, it means that the starting metal is a primary alcohol. Thus farnesol is a primary alcohol. And since it is a primary alcohol, we can rewrite the molecular formula of the farnesol like C14H23CS2OH. So in this way, we have progressed a lot as far as the structures of farnesol is concerned. We have proved the 3 degree of unsaturation and it corresponds to 3 double bonds, and we have also find the nature of oxidation. It's in the form of primary alcohol. Now in this structure where 3 isoprene are joined together, in this structure we have to find out the positions of these 3 double bond as well as the positions of this OH group, and for that this degradation experiment is performed. Now here farnesol is subjected to oxidation, it gives a farnesol. Farnesol on reactions with the hydroxylamine, it forms oxime, and this oxime undergo dehydration in presence of acetic anhydride and we get a nitrile compound or a cyanide compound or a cyano compound. And this cyanide on hydrolysis gives us farnesic acid with the same number of carbon atom hydrolysis. But during the same experiment, we have got another product with the 2 number of carbon atom less than that of the starting material, and its formula was C13H22O. The analysis of this compound has shown that it is a ketone, and it's more specifically it was found to be a geranyl acetone. It was found to be geranyl acetone. Now the formations of geranyl acetone from this is possible only when we assume the structure of 3 as this one. That's alpha beta unsaturated nitrile. And alpha beta unsaturated nitrile is possible only when we assume this molecule as a alpha beta unsaturated aldehyde. And alpha beta unsaturated aldehyde is obtained from farnesol. It means that farnesol is an allylic alcohol. So on the basis of this experiment, we reach to the structure of farnesol very quickly, and we have to now again convince ourselves how this sequence is working. We have got this 13 number of carbon atom. There are 2 less carbon atom than the starting compound number 3, and here farnesol on oxidations gives farnesyl, its reactions with the NH2S gives oxime, and its dehydrations with acetic anhydride gives nitrile. And nitrile is an alpha beta unsaturated compound, and there is a characteristic reactions of alpha beta unsaturated, that is a retroaldol condensation. So chances is that 3 undergoes retroaldol condensation, and we got here geranyl acetone. So chemists were having very good understanding about the geranyl acetone, and since they reached to the structure of geranyl acetone, they reach to the structures of farnesol very quickly. So in this way, we have proved the structure of farnesol. Now another proof regarding the structure of farnesol comes from the ozonolysis in the same year 1913. When ozonolysis of farnesol was carried out, then 3 products were obtained. That's a levulandate, acetone, and glycoldate. Now in ozonolysis, the carbon-carbon double bond is replaced by carbon-oxygen double bond. So here there are 3 double bonds, and 3 double bonds are cleaved, and we get the 3 different products here. One is levulandate, and levulandate is obtained from this bond cleavage as well as this bond cleavage, and this acetone is obtained due to this trisubstrate cleavage of this trisubstrate double bond, and here we get the glycoldate due to the cleavage of this double bond here. So in this way, we have reached to the structures of farnesol molecule, and in structure determinations we have dealt with a very simple chemistry. We have done the hydrogenation experiment. From that we got how many double bond it contains. It also forms a monoacetate derivative, therefore it is an alcohol. This on oxidations gives an aldehyde, and then formations of geranyl acetone was accomplished through oxime formations followed by dehydration and the retroaldol type of the condensation, and at the end ozonolysis has provided additional support for the structures of this farnesol molecule. Now in this way we have learned the structures of farnesol. Now it's time to discuss the synthesis of farnesol. Laboratory synthesis of farnesol is considered as another evidence for the structure proof of the farnesol. There are 2 syntheses of farnesol reported in the year 1913 and 1967. E.J. Corey proposed the synthesis of farnesol. Now in both the syntheses, the starting material is a geranyl chloride. Geranyl chloride is treated with the ethyl acetate. We get a geranyl acetone. our requirement is 15 number of carbon atoms, and the 10 number of carbon atoms are coming from geranyl chloride. This substrate can be obtained from chlorinations of geraniol with thionyl chloride. So geranyl chloride on reactions with the ethyl acetate gives us geranyl acetone, and the additional 2 number of carbon atoms are provided either by formaldehyde plus lithium dimethyl cuprate, and it leads to 15, or alternatively in the year 1913 geranyl acetone was treated with acetylene in presence of sodamide, and we get here farnesol molecule. So 3 number of carbon atoms is coming from ethyl acetoacetate, 2 number of carbon atoms is coming from acetylene, and in this way the 15 number of carbon atoms in geranyl is assembled. Now let us see first synthesis published in the year 1923. They starts from geranyl chloride treated with ethyl acetoacetate. Base catalyzed alkylations of reactive methylene compound occurs, and then this beta ketoester undergo hydrolysis and decarboxylations. We get a geranyl acetone. So in this way we reach to the 13 number of carbon atoms. Then this 13 number of carbon atoms reacts with the acetylene molecule, and we get a tertiary allylic alcohol. This tertiary allylic alcohol undergo allylic rearrangement, and we get a farnesol. So this rearrangement of nerolidol to farnesol, is considered as one of the evidence in support of the structures of farnesol. Now this rearrangement of nerolidol to the farnesol is an allylic rearrangement, and it is analogous to the rearrangement of linalool with the geraniol. Linalool is also a tertiary allylic alcohol. Nerolidol is also a tertiary allylic alcohol. Both of them undergo allylic rearrangement, and we get a farnesol, and we also get here geraniol. So the mechanism of this, both the reactions, a carbocation mechanism, and it is proceeding through the allylic shift. Now the second synthesis is again starting with the geranyl acetone. We have seen how geranyl acetone is obtained from geranyl chloride as well as ethyl acetoacetate. Then it is treated here additional 2 number of carbon atoms is coming from formaldehyde, and it is coming from coupling reactions of Gilman's reagent, that's a lithium dimethyl cuprate. Here the oxygen is removed by treating with the PCl5, and we get a geminal dichloride. Lutetium is a hindered base. 2,6-dimethyl pyridine is a structure of lutetium. So in presence of a base, it gives a geminal dichloride. This geminal dichloride undergo double eliminations, and we get a sodium acetylide. Sodium acetylide is a carbon nucleophile. It reacts with the formaldehyde, and we get a propargyl alcohol. Propargyl alcohol on reductions with the lithium aluminum hydride and reactions with the molecular iodine use a vinyl iodide. And this vinyl iodide undergo coupling reactions. sp2 carbon couples with the sp3 carbon, and it is called as a Gilman's reagents, and we get here farnesol molecule. This synthesis was published in the year 1967, and it was published by the group of Corey, E.J. Corey. Now in this E.J. Corey synthesis of farnesol, this reaction is very interesting. That's a reductions of propargyl alcohol to vinyl iodide. Here, first of all, reactions of lithium aluminum hydride occurs with hydroxyl group, and we get a aluminum oxygen bond with the liberations of hydrogen. And then this tetracoordinated aluminum offers here hydrogen in the form of hydride, and here we get a negative charge. This is a sp hybridized carbon atom, so to some extent this hydrogen is promoted, hydrogen transfer is promoted, and then we get a heterocyclic compound with aluminum as one of the member. This negative charge is trapped by the aluminum. Its coordination occurs here, and later on iodine cleaves this heterocyclic complex, and we get a vinyl iodide. Now last, let us see about the cis-trans isomerism in farnesol. These are the two double bonds where cis-trans isomerism exists, and there are various possibilities. These two double bonds can be trans. Here is a CS2 is trans. CS2 both of them are trans around this double bond. One can have a CS2 cis around this double bond. CS2 around this double bond. Then this is a CS2 around this, and here is a CS2 they are trans. So one can have a trans cis as well as cis trans form of the farnesol, as well as trans cis form of the farnesol. So there are 4 stereoisomers of the farnesol. So in this way we have learned the chemistry of farnesol molecules. We started the structure determinations with the help of very simple chemicals, simple experiments, and varies to the structures of Farnesol molecule. We have performed hydrogenation, oxidations, and we have obtained geranyl acetone. The formation of geranyl acetone was a major clue in reaching to the structures of Farnesol. We have performed the ozonolysis. And then in the subsequent discussion, we have prepared Farnesol molecule from geranyl acetone, and here two methodologies are involved. One is acetylene chemistry and second one is a Gilman's reagent, as well as the reactions with the formaldehyde. Nerolidol undergo allylic rearrangement with the farnesol. It is considered as one of the evidence for the structures of farnesols, and we have seen this reductions of propargyl alcohol by using lithium aluminum hydride. Here heterocyclic type of the compound is obtained, aluminum heterocycle is obtained, and then it's cleaved with the iodine to get the vinyl iodide. And at the end we have seen how farnesol shows the stereoisomers. So in this way we have discussed the chemistry of farnesol molecule. Now once the chemistry of farnesol is learned, we have to check our progress by solving the number of problems. Here some of the problems are mentioned. The formations of geranyl acetone is a major clue here, and therefore here this reaction sequence is uh, indirectly asked in the form of a problem where the molecular formula of the intermediate is shown. A student is supposed to undertake this exercise to write the appropriate structures of these intermediates. Second one, what are the products of reactions of farnesol when it is treated with each of the reagents? We have seen all these reactions in the structure determination, so this is also a very interesting problem. Then another one is about the synthesis of farnesol. This is the EJ-Corey synthesis of farnesol. Here the reductions of propargyl alcohol using lithium aluminum hydride is involved. Therefore, this is also very important reaction sequence. Students should undertake it as an exercise. And at the end, there are three mechanisms. These two mechanisms are allylic rearrangement, nerolidol to farnesol, linalool to the geraniol. Both of them involves a allylic rearrangement. Both of them involve a carbocation rearrangement, and the last one is related to the reductions of the propargyl alcohol by using lithium aluminum hydride. So in this way, we have learned about the structures of farnesol molecule. In the next lecture, we'll discuss about the structure of zingiberine molecule. Thank you. Thank you very much for watching the video. Thank you.